All right, so this is part 5 to the section 4.1, and this part of the section, I wanted to introduce the concept of solving a differential equation. Because if you're going engineering or maybe just physics, you're a physics major, you will have a differential equations course. And so what I'm about to go over is just a preview of what solving a differential equation incorporates. Now this is like a baby down version. It's just different techniques in differential equation courses that you'll use that are more complicated. So from the first video of this section where we introduce the concepts of the antiderivative and indefinite integration, we were asked to find a function whose derivative is f of x equal to 3x squared. And we got such a function where our solution was capital F of x equal to x cubed plus c. And we had this plus c because that was giving us a family of functions which I ended up calling is the general solution. And we added this c because c can be any constant. So for instance, you could have had capital F of x equal to x cubed plus 4. That's going to give you the derivative being 3x squared, because you take the derivative f prime of x all right, so apply the derivative rules. X cubed by power rule, that becomes 3x to the 3 minus 1, which is 3x squared. And then the 4 goes away because that's a constant. So it's 0 for the derivative of 4. So that's why you get 3x squared. And now we have c. C can be just any constant, any value you want. And it'll give you that same derivative. So that's why it's called a family of functions, since c is allowed to vary. And I just said note f prime of x, take the derivative of x cubed plus c, you get that same thing, 3x squared, because the derivative of c is 0 since c is a constant. Now really, technically this is solving a differential equation. I just didn't explicitly said so when we went over this. And we just talked about what the solution was. All right, so that was the first video. I presented this problem. We wanted to find a function whose derivative is 3x squared. And then I said, well, this function is capital F of x equal to x cubed plus c. Now the question is, how do I get that function, x cubed plus c? And that's called the general solution. So what I'll show is the steps you would do to find that general solution. So first, say, as a differential equation, the example can be written as the following. It could be written as, you commonly see it as dy dx equal to 3x squared, or f prime of x equal to 3x squared. Those are just two common ways you'll see the problem written, and you just need to find the general solution. You still do the same methodology. So in yellow, I just wrote, how do we find that general solution? We find it by getting the antiderivative, which led to the discussion of finding indefinite integrals. And like I said earlier, I just said what the solution was. And here we'll actually work out the problem, the steps. So we can solve the differential equation to get our general solution by integrating. And here are the steps that are done. So our original problem, so I'll show for both ways, or both ways you see it, dy dx equals 3x squared, and the other one, f prime of x equals 3x squared, still the same kind of thing. So first one was dy dx equal to 3x squared. And what I do is I bring the dx over to the right side with the 3x squared, since it's the variable's x. So I keep the dy by itself on the left side so that I have the variable of integration being y on one side and the variable of integration x on the other side. So that's the first thing I do, is I bring the dx over to the right side. Then I integrate both sides. So that's what you see in green. I put the integral sign. Now, we know the right side, when you integrate 3x squared, just based on our integration rules from previous videos, you do 3 times the integral of x squared. And integrating x squared, you add 1 to its exponent, so that's x to the 2 plus 1, which is 3. And then you divide by that same value, divide by 3. So that's why you have 3 canceled out with 2 plus 1, since those are 3 top and bottom, you get x cubed plus c. Now the left side, you see I have y. So when you integrate dy, that is sort of what I have written here. And it's based on the rule when we integrate k times dx, where k is just any constant, it turns into kx plus c. So in this case, specifically, if you have just the integral of just dx or the integral of dy, that's the same thing as just writing it as 1 dy. So our value is k is 1. So that becomes 1 times y. So that's where the y comes from. All right, and so this way I have my answer, general solution, is y equals 2x cubed plus c. And earlier I wrote it as capital F of x equal to x cubed plus c. It's the same thing. We use a variable y in place of the f of x. All right, so that's how I treat it, as if it was dy dx. So sometimes the problems, instead of written as dy dx, it'll be written as f prime of x equal to 3x squared. So the concept of integrating both sides is the same. So I put in green the integral sign, and then I also put the dx to reinforce that we're integrating both sides, and this time the variable integration is x. So it's dx on both sides. Because our function on the left side, f prime of x, has x as its variable. All right, so right side's all the same. We just integrate 3 times x squared, and that became 3 times x to the 2 plus 1 divided by 2 plus 1, which we divided out the 3's to get x cubed plus c. And then on the left side, you see that I replaced the integral of f prime x dx with just capital F of x. All right, so I've essentially got rid of the quotation, single quotation mark, which that quotation mark means it's the derivative. Right, so I got rid of the derivative sign for that function. And that's because integration is the inverse of differentiation. And so this is actually in our textbook, is that anytime you integrate the derivative, f prime of x, dx, you get the function just back f of x. All right, so that's why I replaced this with just f of x. All right, and then you'll have f of x equal to x cubed plus c. So it's the same answer as this, y equals x cubed plus c. It's just instead of y, I have f of x. And the concept is I integrate both sides. It's just this one looks a little bit more funny because I have the dy dx notation, and then I first put the dx on the right side, keep dy on the left side. Whereas this one, I just go ahead and just integrate both sides from the get-go. All right, so here are some examples, and I'm going to find the general solution to the following differential equation. So they're similar to the ones I just did. There's 4 examples. First example is example 1 on page 249. And then I made up an example called my example. And then there's 2 other examples that are in the homework section of the textbook. So the odd problems, I had number 7 and number 9. All right, so that's what this video, I'll just focus on solving these 4 differential equations. And again, our answer, in this case, x cubed plus c, that's called a general solution. So we're dealing with finding general solutions in this video. All right, so for this first example one on page 249, you have dy dx equal to 2. So I'm going to solve this differential equation like I did for this one, where I had dy dx equal to 3x squared. And so the first thing I'm going to do, like I did in here, is I brought dx to the right side. So that's the first thing I'm going to do, is bring dx to the right side. So I'll have dy on the left side equal to 2 dx. All right, then I integrate both sides. So I'll just go ahead and write dy and then 2 dx, and now I'm going to attach an integral sign. So I integrate the left side, integrate the right side. So integrating dy, that gives me y, all right, because of what I had earlier. Integrating like k times dx gives you kx plus c. It's just for dy. You could write it as 1 times dy, which will give me 1 times y plus c, so which is y. And notice I don't write the constant of integration with it. I just go ahead and put the constant of integration on the right side with the x. So I have y by itself, and that's fine. You don't have to put the constant of integration in this case with the variable y. So for integrating 2 dx, I factor out the 2, so I'm integrating 2 and then the integral of dx by the same logic as how I integrated y. This becomes x, so it'll be y equal to 2x, and then plus my constant of integration c. All right, so that's my general solution, y equals 2x plus c. All right, so that's that one. Now I'm going to do the one that I have as my example, f prime of theta equal to 3 times theta. All right, so this case I have f prime of theta. It's a function of theta. And so how I did it earlier was I just went ahead and integrate both sides. And when I integrate both sides, I put a dx because our variable is x. And in this case, our variable is theta. So I'm going to integrate both sides, but have a d theta. Let me add some more space. Integrate that. Integrate that. Now the rule is if you integrate the derivative, you get back the original function, I like to call it. So like here, I had capital F prime of x, integrated that turns in that capital F of x. I get rid of really the quotation mark, which means get rid of the derivative sign. I'm going to get rid of the derivative sign. So it's just f of theta integrate equal to 3 times theta d theta. And you could factor out the 3. So you're integrating 3 times theta d theta. And I'm using that rule that I've used in the previous videos. So you add 1 to its exponent, and then you divide by that value. In this case, our variable is theta. So it's going to be f of theta equal to 3 times, and it's theta to the 1 plus 1 divided by 1 plus 1, and then plus c. So that's 3 halves. So f of theta is equal to 3 halves theta squared plus c. All right, that's the general solution for this one. All right, so it's just all relies on integrating both sides. It's essentially what's going on. All right, so number 7 has dy dt equal to 9t squared. All right, so I go ahead and bring the dt over to the right side since I have 9t squared on the right side. That gives me dy equal to 9t squared dt. All right, so then I have the dy on one side, I have the dt, so I have the variable y on the left and the variable t on the right. So I'm going to integrate both sides. Integrating dy gives me just y, and then equals, and then 9 times the integral of t squared dt. In this case, my variable of integration is t on the right, but I still apply that same rule where you add 1 to the exponent and divide by that value. So it's going to be y equal to 9 times t to the 2 plus 1 divided by 2 plus 1 plus c. So that's 9 divided by 3 is 3. So it's going to be y equals 3t cubed plus c. All right, so this stuff shouldn't be too complicated because I dealt with more complicated integrals in the previous videos. All right, so just add 1 to 2, that's 3, and then you divide by that same value. 9 divided by 3 is 3. All right, now the last one for this video, number 9, is dy dx equal to x to the 3 halves. So bring the dx to the right side. So I have dy equal to x to the 3 halves dx. Integrate both sides. Integrating the left side, the integral of dy just gives you the variable y, and then equals, and then I do that same rule where I add 1 to the exponent. It's going to be x to the 3 halves plus 1, and then divided by that same thing, 3 halves plus 1, and then plus c. So what's 3 halves plus 1? That's going to be 5 halves. So you have y equal to x to the 5 halves. And you're dividing by 5 halves. That means you multiply it by its reciprocal. So dividing by 5 halves is the same thing as multiplying by 2/5. All right, and then that's going to be my answer. All right, and all of these dealt with having a plus c at the end. Had a constant of integration attached to it. And that's because these were general solutions to the differential equations. And so the next video will cover differential equations with particular solutions. I'll just do DIFF and then EQ for differential equations, and then with particular solutions. And it's really the same steps. There's just an added couple steps thrown in there. All right, so that's it for this video.